we've ended the last video with this equation right here, where we were trying to solve this equation for the norm of the gradient vector, and we've solved that in here, and we've called that equation number 2. So if this one here is equation number 2, so what is equation number 1? That's a good question actually, and here it is. That's equation number 1, as w minus et. Yeah, we wrote this down in the last video, but actually just like we're rewriting this here for the sake of completeness, because we're gonna use this. Now actually we've got to the point where we're gonna discuss the core point of Schrödinger's work. And if you think it's like, a hell of a math, no, it wasn't. It was an observation. And actually that observation, the irony is, that observation has been done 100 years before him, even by Hamilton. But actually Hamilton didn't take any action regarding the observation, and it was Schrödinger who took the action and got us the equation, and he got the Nobel Prize, and he got the fame forever. Okay, so let's get started. Actually what Schrödinger did was the following. He said, okay, let's assume for a moment that this action function is a constant. Let's assume it's a constant which is equal c, right? Okay, now what? We know actually from calculus, and Schrödinger's already did, and I'm sure about that the gradient of s is gonna be orthogonal to s equals c. Do you know about that? With the theorem, I'll write it down here if you remember about that. If you have f of x of y and z, and that function equals c, then you have right away the gradient of that function at the point x naught, y naught, z naught, orthogonal to this curve, equal, we call it the level surface at this point. So that was the theorem actually. So that's the thing. So now we know, and Schrödinger did actually already, and he got the equation, so he did know about that. The s equals c, right? And gradient s will be orthogonal or normal or perpendicular to s equals c. Okay, now what? Okay, I'll try to write down here that one equation, last equation. I have to remind you of this. Do you remember the partial s partial q equal p small? Do you remember this equation? Actually, this equation is nothing more than the gradient s equal the vector p. That's really amazing. You're gonna see the amazingness of this result in a moment. That's amazing. So this means p is normal to the surface of constant action. That's really huge. That's the observation. That's really the observation. To see this more clearly, we have to plot the following. Assume for a moment that the following is the plot is right here. Is the plot of the level surface of constant action at time t. At time t plus dt, that is after an elapsed time dt, will have the same action. The action is not changing. And for these curves here, or those level curves here, we'll have those vectors. Those are the momentum vectors. They'll be orthogonal all along. All the time they'll be orthogonal to those surfaces of constant action. That's really huge. That's really huge, and you're gonna see why in a moment. So what's the implication of that? The implication of that is that we can draw, or we can construct all the different possible mechanical trajectories which are gonna be orthogonal to those surfaces of constant action as well. That's really amazing. That's really amazing. Actually, this point of view is identical in its core base to the point of view in the geometric optics. Do you know about that? In optics, we have the rays, which like represents the different electromagnetic waves. We like, as a limitation, we simplify that to rays, and those rays are all the time orthogonal to the surface of constant phase. So light can be represented in the geometric optics as rays, which are all the times orthogonal or normal to the surface of constant phase. So the two point of view is identical in their core base, right? In their construction. And that's the point. That's really the point. You didn't need anything further to just to derive all the greatness Schrodinger did. What you need to know is that this point of view here in the ray optics is a limitation to a more general formulation, which is called the wave optics. So that tells us from this analogy that this dynamics as being represented by the Hamilton-Jacobi equation is a special case or a limitation as well to some more general wave mechanics. And that's the point. That's the observation, and that's the conclusion, and the rest is just math. So that's all what you need to know to be able to get the equation like Schrodinger did. Thanks for watching. That will be it for this video, and I'll continue in the next video. Thanks for watching.